Hello, so I wanted to do a second lesson on classifying systems of equations. So this is following the little lesson I did, on graphing systems of equations and finding the solutions graphically. So first off, we have two different possible representations of a system of equations, right? So if we have a system of equations, we could literally have the two equations written. Like, for example, y is equal to 2x minus 3, and say 5x plus 2y is equal to 17. So that is a system of equations, any pairing of two equations. We could also have another representation, which would be the graphical representation, which would be we're not necessarily given exact equations, but we're given a picture that could look something like that. And that's a system of equations because we have two distinct lines that may or may not intersect at some point. So we have equation representation and we have graphical representation. So it can be very helpful to classify a system of equations so that we know about how many solutions it has, what it might look like, and that's what I'm going to go over today. So let's push this aside. So first off, along comes a system of equations. Our first choice would be, is it consistent or is it inconsistent? So a consistent system of equations has at least one solution. So that is our definition of a consistent system of equations, is a system of equations with exactly one, or at least one solution. So now, if we have an inconsistent system of equations, that would be a system of equations with zero solutions. So first we'll go over inconsistent. So how could a system of equations have zero solutions? So as we went over in the last lesson, the solution to a system of equations graphically is the point where the two lines intersect. So what is the only situation in which we have two lines that do not intersect? That would be parallel lines, which, as we discussed earlier, they're lines that have the same slope. So graphically, an example of an inconsistent system of equations could be anything that looks kind of like this, with two parallel lines with the same slope, because they're never going to intersect. There's no point that both of these lines have in common. So a consistent system of equations, as we went over, it's a system of equations with at least one solution. An example of that graphically could be just something like this, a line that goes like this and a line that goes like that, because you see it has at least one solution, which this particular one has exactly one solution, which is right there. So what do these look like with an equation representation? So an inconsistent system of equations would be two lines that are not the same but have the same slope. So you could have y is equal to 1/3 x plus 5, and y is equal to 1/3 x plus 3. So again, there are so many possibilities for examples of inconsistent systems of equations. What's an example of equations of a consistent system of equations? That could just be any two lines that do not have the same slope. So we could do y is equal to 2x plus 10, and y is equal to negative 1/7 x minus 3. Because those lines are going to intersect at one point. So we have our system of equations. If it's inconsistent, that's kind of our end game. We just say, okay, the system of equations is inconsistent, and that's how we classify it. But if we have a consistent system of equations, we have another branching point. So it could be either independent or it could be dependent. So what in the world is the difference between independent and dependent? So an independent system of equations has exactly one solution, whereas a dependent system of equations has an infinite number of solutions. So you might be asking, how in the world can we have an infinite number of solutions to a system of equations? And that is a pretty good question. It's one that I think I asked myself in high school. And that would be if we have two lines that are exactly the same and overlap. So you get just a thick line because there are two lines overlapping, and it would look something like this. Because a solution to a system of equations is a point that both lines share, and these lines, as you can see, they share an infinite number of points. So where this gets a little bit tricky is when we want to figure out if a system of equations that is represented just with the equations of the lines is dependent. And an example of that would be, let's say, y is equal to 3x minus 10, and then say y is equal to 12x minus 40. So 4y is equal to 12x minus 40. So the reason that this system of equations is dependent is because if we divide the second equation by 4, divide both sides by 4, because as we know, if we divide one side of an equation by a number, we have to do it to the other side to preserve the equality, we will get exactly this same thing. So even though we have two different looking equations here, they actually represent the same line. And if we were to graph it, we would get a situation like this, where we have the lines overlapping. So that is a dependent system of equations. An independent system of equations is what we dealt with in the last video, where the lines will cross at one point. And that is probably the most common system of equations that we will see. And that would look graphically something like this. The lines cross at one point. And then with equations, those would again be any system of equations that has where each equation has a different slope, and where the equations cannot be manipulated so that they are the exact same. So those are just some examples of how you would classify equations. So again, we get an equation. If it's inconsistent, if it has no solutions, that's the end game. So we just call it there. If it's consistent, we need to classify it as either consistent and independent or consistent and dependent. So yeah, so that's just how you do it. And in our next lesson, we will go further on solving systems of equations, and we will go over solving systems of equations by substitution method.